let's do the last question of the tutorial, question 5. Okay, so they already told us that there is a thick wall, so definitely we're going to use thick wall. A thick wall cylinder is made of a steel with this particular stuff. Inside diameter 20 mm, outside diameter 1 mm, 800 mm, what am I saying? And then cylinder subjected to internal stress, so it's within the system that is coming out. Alright, and we normally would assume that the outside pressure is always equals to 0. Okay, so far so good. And determine the stress components in terms of axial, radial, and hook. Alright, at R equals to RO, meaning the outside radius and the interior radius. Alright, the first thing that comes to my mind is, when we are talking about thick wall, we are going to use these formulas. Alright, this is the radial stress, if you remember, sigma RR. This is the hook, this is the axial or the longitudinal stress. And if taken that pressure outside is equals to 0, this means that the whole equation here is 0. Alright, it's not that how do I say, it's not that, okay, maybe PI is over here, so I assume that P out is 0, so I continue to calculate. Alright, don't do that. Alright, if you do that, it's a waste of time. Alright, if you're gonna go one big round, alright, based on this outside pressure, you're gonna come back the same pressure over here. Alright, you're gonna come back with the same pressure over here. So I'll highly not recommend. If you want to do it, you want to prove, you can just prove it yourself. Otherwise, I can straight away sub in sigma RR. Alright, if it's in terms of, okay, never mind, let's just start off first and then you'll see how. Alright, just remember that this is only part A. Later on we'll go to part B. Alright, just hang on first. Alright, so they call us to actually find in terms of R is equals to R out and R is equals to R in. So if you were to just take a look clearly, there is some form of a R over here. Alright, hold on. In fact, we should also choose this formula. Alright, it's only within, I actually forgot to say, is that if you're talking about only internal pressure or only external pressure, if either one pressure is given only or the other is equals to 0, you can just straight away use this formula. This whole chunk of formula is talking about when you go pressure in and pressure outside. Alright, then you're going to use this chunk. Alright, if you were to sub in 0, if this is, of course we know that internal pressure is 300 MPa, if you sub in 0 over here, later on you will still get back something with what you have found over here. Okay, later on, so that's why you can actually look back to the video that I look at l5v4 deriving stress. You can look at this video. Alright, it will prove everything to you, I believe. Let's just analyze things in terms of this easier form. Okay, while the sigma ZZ is still the same. Okay, so as I said earlier just now, the R for this case, alright, you have to do two things. Alright, in terms of RI and RO. Okay, so I'm gonna split into two stuff. I have an internal radius R and an outer radius R. Okay, so in this case, internal I'll just sub in as RI. Alright, simply sub in as RI over here and RI over here, and this over here I'll just sub in as R out and R out. Okay, while the sigma ZZ is, if you take a look, there is no R in here. Alright, so sigma ZZ for internal or external, they're always the same. So I can just calculate one time. Alright, so therefore their equations are the same for internal or external, their radius. Alright, because sigma ZZ is the longitudinal, is this portion over here. It does not is not affected by the radius, and therefore and this explains why they are the same for both analysis for outer or internal radius, because it is totally not affected by radius at all to the extent. Alright, so if I were to solve for this, alright, Ri over here now, so I can just simply cancel Ri and Ri over here because they are actually the same. Alright, so I'm doing for the internal radius now, okay, because this is the one that they want us to do. Okay, and the pressure, actually we don't need to calculate sigma RR because we say that sigma R, if it's in terms of if it's a pressure in only, alright, it's just equivalent to sigma RR, because if you take a look, there's a cylinder over here, there's a pressure acting all against the side, right? The purpose of sigma R, the radial stress, is to act as a opposing force against the pressure. Alright, so if the pressure is 300 MPa sigma RR is simply the opposite, minus 300 MPa, because we are talking about static. Static, you'll just let this cylinder over here and then let it go, let it go, and just let it go, just leave it there and then let it go. So therefore we can straight away straight away know that sigma RR is equals to minus 300 MPa. Okay, while this one is equals to 0 MPa. Why? Okay, this is outer radius. Outer radius we're talking about, because we know that outer radius is 0, right? So there is no pressure outside that is acting on our system. So therefore there will also not be any radial stress acting against this pressure. Alright? Or in other words, if you were to just take a quick look, is that I forget one thing, is that there is also another Ri over here. Alright? That's Ri and Ro. Right? By the formula itself, you see Ro square minus Ro square, because it's outer radius, this whole thing becomes 0. Anything you divided by 0 is 0. And this explains this. And therefore by formula and by explanations, these are all legit, all true. Okay? So we have already solved for our radial stress. Straightforward. Alright, but so please remember, when you are given only the internal pressure, there's no outside pressure, you can just straight away use that one and then to the negative side. The sigma RR is just simply the opposite. Alright, if you're having the internal one, the external one, which is talking about pressure in and pressure out, alright, this one, then things got a little more hairier. So be careful of which formula you're going to choose, alright, in during exams. Alright, so now let's continue to internal radius, alright, for the sigma theta theta, which is your hoop stress. Hoop stress, this is Ri square I can still cancel. Alright, so I left with this is Ri also, because it's internal radius. I'll just simply sub in the stuffs over here. So it's 300. Alright, it's not negative because this hoop stress is not acting against the pressure now. This hoop stress is just simply its own self. Alright, it's just, okay, I think I'll not explain, this is just straightforward. Alright, so this is in terms of MPa, which is Newton per meter square mega. Alright, so therefore your radius has to be in terms of meter. Alright, so it's the inside diameter. Alright, so it's 10, because it's 20 divided by 2 is the radius. Alright, so 10, because we run our radius over here, 10 divided by 1000, alright, the whole thing square. Alright, I zoom in a bit. Plus the outer radius, which is, if you just take a look, is 100 mm diameter, so the radius will be 50 mm, right? Just divide. So our stuff is actually 50 divided by 1000 square, because they are all in meter, and this is meter square, this is mega Newton per meter square. Alright, divided by the R and minus R in, I just simply sub in only. I have this over here. Alright, you can just do it if you're free, alright, or if you feel that you are feeling unsafe. Alright, these are all meter square, because they are just meter to the power of square. Alright, so this thing will cancel out each other. So what you have back is only going back with the MPa. Alright, so I'll just solve for this, so hold on a while. Therefore this is 325 MPa. Alright, it's just this numerator is this value, we can just verify, and this is this. And I may have potentially careless mistake. Alright, just take note. Alright, but seems nice because the number is like, it's very nice, 325. Alright, and now similar thing, I'll just happen to solve for our outer radius. Alright, because this is talking about the outer stuff. I'll just simply sub things in. Alright, I'll not do with you, so I'll just simply put the numbers now. Before I solve for this, I realized something you may need to take note, is that you see Ro square minus Ri square, Ro square minus Ri square. So during your calculation, you can actually skip step, because once you know this value already for this part. Alright, this part is the same thing. Alright, so you just sub in over this value over here can already. Alright, and it's quite straightforward. Alright, same as for if you are required to calculate the radial stress. Alright, their denominators are all the same if you to compare. Alright, it's just between the inner radius and the outer radius of their own area, that's all. Just talking about that particular area, and that's just the meaning. Alright, I'll just continue to solve for it and hold on. So what I would have is only here. Alright, this is the numerator and this is the denominator. I'll just multiply, and what I have is 50 MPa. As you can compare, this is a huge difference between the outer and the internal. Alright, so for thick wall, normally I will highly recommend you do for the outer and the internal radius, so that because of their huge difference in terms of the pressure that is acting against the internal radius and the external radius. Alright, I mean not in terms of like straight away like that, it's in terms of a very deeper meaning in terms of their radial stress, I would say, more on that a particular exterior and internal radius type of stuff. Alright, yeah. Just to take note, the blue color one is the exterior, the red color one is the interior thing. So you just go into a circle right here. Alright, this is just the exterior and the interior stuff. Alright, and therefore because the blue color has a more surface area, so it actually takes in lesser stress. That's why you will infer from. And from the internal one, because it's a smaller piece, therefore it will take in more stresses. And this is how I infer. I may be wrong, but sounds kind of like legit. But anyway, this is the two for our. These are the two values for our radial stress. Now let's solve for our sigma ZZ, our longitudinal or our axial stress. Let's go. Just take note the longitudinal stress is always the internal one. Alright, it's always the internal one. Even if you have a external pressure that is coming in, the longitudinal is only talking about this lies over here. Alright, this whole line, I would say, the whole axial line that is talking about it, because it's trying to pull at this direction. Alright, so to speak. But anyway, let's just continue first. Okay, so what I have is okay, sorry, my fault. What the hell am I talking? They have a pressure outside also, but in this case this pressure outside is 0, so this whole thing becomes 0. Alright, so sometimes what I say may be wrong lah. So yeah, definitely lah, because I not cool. Alright, just write it down, all the stuff. Alright, this is just simply the same as this, right? So I'm just taking this value over here, because what I've calculated over here is simply this value. Okay, and this thing is the same as this thing, as I say, so I'm just simply taking that value. Okay, what I will calculate now is, yeah, so comparatively this axial stress is like a mile, very small, only 1.25 MPa, compared to those is like very huge. Alright, so let's just compile everything. Alright, let's make things more easier to see. Okay, so here we are. We can compare now the internal radius and the outer radius. As you can see, the internal one actually subjected to more stresses comparatively to the outer one. As you can see, right, it's more apparent because the internal one has gases that is more pressurized, while the external one has no pressure acting against it. So relatively, the radial of it further and further away takes in lesser stress. Alright, therefore it's kind of cool. So because your outer radius will actually tahan more of the stresses. I mean, although these stresses are subjected stress. Alright, these are all only subjected stress, so they are only subjected to due to the certain internal pressure, and that's all. It's not talking about the material stress. The material stress is the stress that breaks it, right? Or talking about the yield strength. So be very careful of what the terms are. These are all the stresses that your cylinder will be subjected to. Alright, so let's just write in terms of a principal stress, because these are all principal stresses now. Right, because they are all just hydrostatic, if you still remember, because it's just pressure and water are all just forces acting on the perpendicular plane, that's all. Alright, there's no shearing. So let's just write in terms of a matrix. So therefore the first value will be the largest value, 325. Alright, the second one will be the middle one, which is 1.25, and the last one will be the smallest one, minus 300. Alright, MPa. Okay, next, for this outer one, I'll have 50 over here, the maximum, 1.25 over here, and 0. Alright, and MPa. Okay, And now let's go to the next question. Okay, don't macam muni. Take a look with a vessel over here, and you may have a crack. Alright, now let's just take this slice of the crack, alright, and put it over here. If I were to take this slice of the crack, I'll have something like this. Maybe it should be bigger or bigger. Something like this. This is the crack. Alright? And this is a crack length A. Alright? I actually give you the steel fracture toughness over here, 50 MPa square meter, and they actually ask you to find this crack length. Alright? So in order to find this crack length, you're gonna find the worst case scenario that will crack the create a crack, right? So the worst case scenario is the largest stresses that were acting on upon your stuff. So it's your 3 to 5, right? Because comparatively, all this value, our 3 to 5 is the most scariest one. Alright, so we'll just subject it to a 3 to 5 tensile load, because this is the largest tensile load. If you remember, the largest value is always the tensile load. It's pulling this and ripping this apart. Alright, and therefore we're going to apply this load over here, 3 to 5. Alright, so let's compare. So this is the yield strength, and this is our formulas from our fracture toughness equation. This is our so-called as tensile stress, sigma 1 from our internal radius. Alright, let's just simply rearrange. Now I can get A is equals to have a 0.074 meter, which is approximately, if you were to times 1000 to change to meter, you have to millimeter, you have 74 millimeter or 7.4 cm. Something, if you were to look at this screen now, is something like this. You can have this large of a crack. Wow, and it can be either my calculation has something wrong, or this question is really weird. So definitely I am something wrong, because 100 millimeter outer radius and 40 millimeter diameter. Right, I mean 200 millimeter, 100 millimeter diameter and 20 millimeter interior diameter. And then so this is 100, and you can have a crack length of 74 millimeter, and okay, I don't know. Alright, but anyway, this is some sort of the calculation. If I have something wrong, at least the concept is always there. Alright, stress on is that this 7.4 cm, alright, is the crack length that we are talking about, this length over here. So anything larger than this, you're gonna rip this apart. Alright, you're gonna have the stress pulling this, and you're gonna extend this crack further. So when you operate in terms of these stresses, be very careful about that. Alright, you may wonder, all along we didn't actually touch on this given parameters, right? E and V. Alright, we are talking all about the derivation, but we actually didn't talk about what is E and V, and why is it here. We don't even use it. Alright, in fact we can use it to derive this equation. Alright, you can use it to derive all this equation. But because we already are given pian, everything is complementary gift, so you just take only. So because this one comes from where? If you still remember our previous very long time ago, the video, we're talking about this thing experiencing a certain stresses, a certain strain, a certain strain along this path. Alright, we talk about strain R and strain theta, the hook strain and the axial strain, and then therefore we will have this particular strain from the Hooke's law. You just sub it in and then do some magic. I don't know how the magic appear, but you get a stress. And then after that, you use these stresses, you sub it in and things like that. You get a general equation, you solve for a general equation, do things like that, and then eventually you get these things. Alright, when you do your, and also when you sub in the boundary conditions, when you sub in the general equations, you are actually putting in the boundary conditions and things like that. Alright, and therefore you derive this formula. Alright, just to touch on before you at least you get a feel. Alright, and in fact the general equation is this thing. Alright, so next time if you ask to derive this thing, you can just use this general formula. Alright, and watch these two videos. L5v4 is the one that is deriving in a more accurate way. L5v6 is also accurate, but in terms of, I don't know what the hell is going on, but at least something to tell you that it is similar to l5v4. but in a strained way, and you should actually look at it. And these are all the stuff from the tutorial. So see you soon.